12th introduction session uh, for this deep learning course, and today mostly we are going to talk about the encoder decoder part. Okay, cool. So just a minute, I have to see one thing. Just give me a moment. Okay, let's start off. Cool. Okay, so before going to talks about encoder decoder model, so we will see that where we are in the journey, and based on that we will go till here, right? So uh, so from starting we have seen basic neurons. From basic neurons we have some artificial neurons, from where we went to sigmoid neurons, from which we went to make a feed forward network, then feed forward with back propagation, feed forward with back propagation, and back propagation having as a main theme. Now we started dividing new different kind of architectures where we deal with convolutional neural network followed by all obviously with back propagation. Now we have seen something called a sequence learning problem. To solve that, we have built some architectures. Basically the theme is recurrent neural networks. Okay, so till now, from here, from very old till recent times, we able to go through this, where we are dealing with each architecture individually, right? So this is how the sequence of for the whole course also, and how this is how it has been developed over the period of time, right? Based on the new problems that we face for a typical uh, machine learning, based on the different type of problems, we are trying to define new type of architectures. Now we reached a stage where now we can start combining these uh, these kind of architectures together, right? And then we start to see that how it will work together. In this case, if we combine 2 or 3 architecture, even with convolution we have seen this part to a good extent, where we have apart from convolution network we have feed forward basically, now which we now call as fully connected layer. Okay, so we have this as a combination of a convolutional network, and we have seen this part right now. But it is going toward us going to solve only one particular task, right? That is, it is a kind of extension of what it's supposed to do. Like convolutional neural network will do certain aspect, and followed by fully connected network will do certain aspect. Now what we are trying to do is we are going to combine multiple different type of network, maybe recurrent with convolutional or recurrent with fully connected and all, but uh, their purpose of having present in that particular architecture will be different, right? So that's where the next step of encoding decoding will come into picture, which we call as encoder decoder. Sorry. Okay, so this encoder decoder will come into picture. We will just have a rough overview of that what encoder decoder will be, followed by we will introduce the attention mechanism. Okay, so these two parts we are going to see today, followed by some code sample I will walk through you, and then we will wrap up, and we will try to discuss with what else you can see, because it's almost end of the course for you. So now after this, where to go for you from here, right? After learning this different type of architectures and all, now what you should do for so that we can have a proper discussion based on that. Okay, so let me quickly go through the encoder decoder model. As we have so let me start with maybe to give certain problems. One simple problem that we have seen earlier also in last time, that in while developing a while developing a RNN, right? So what we are saying is So we have the smartphone, in that we have one we have this keyboard, right? So if I write I, so based on that it will try to predict what is my next state word would be. So I, if it is I'm writing as I as a first word, then it will try to predict am. Okay, if I predict I am at, it will try to predict at, then it will predict home, it will predict today, kind of like that. So this is our sequence to sequence problem, where uh, not sequence, it's simple sequence labeling, or just in a simple term we just trying to predict what is the next word would be, right? So given my so if I want to understand that the word today has to come as an output, I should look at my previous inputs. Okay, and based on that I want to predict this today as a word. Okay, so this is all what we have seen in RNN. So what we are doing here is we start with certain variable, let's say go, which doesn't have any value, but what will pass to it with certain weights, which we are naming as to u, and then we have some states. Now instead of hidden layer, we are saying hidden layer, which we used to call, now we are calling it as states. Okay, now we will it will try to understand this, what this word meaning is. It will take some previous state, some s0 state as a input, and then uh, try to improve the state of understanding of this go keyword. Okay, and based on it, it will try to predict that based on my go keyword what is my output will be, so that is the next word. So this is the prediction it has to do. Okay, some prediction it has to do. Now once it has done, again we are giving them it as I as again as an input. Again we are going with the same process. We are finding some weights to encode this I, and we are passing to a hidden state. Only difference here is, now when I am going to this blue state, I am just trying to also consider my previous state. So in this case, let's say if this is s0, this would be s1. Okay, so then similarly this some output will be predicted, and again it will take as an input, and then again I will consider the along with the previous states. I will try to see, okay, I have am, so I will try to train my hidden state in such a way that it should give me output as at, right? That's how it would be. Now if you try to see this whole part of whole this diagram, now blue I'm creating with blue box. The one thing that I'm doing in seeing this here, I'm doing some kind of encoding. Here what I'm doing is, if I am at this inputs I'm taking, I'm converting to certain in certain dimension within these states, right? So here I'm trying to encode it. I'm not only encoding my current input, but also I'm coding the current input with its previous states. So once I'm encoding, this part comes at encoding, so I'm encoding my current input, right? And I maybe use black here. So the black box here, what is doing, based on my encoding features or the embeddings, I'm trying to predict it. So I'm trying to decode based on my encoding. Okay, so this is what I'm trying to do. So what I can say, actually RNN, you can summarize RNN within these two layers only. You don't even need the upper part. Okay, but upper part you can just say as a fully connected network, fully connected, or feed forward, any such names. Okay, so in even a simple RNN architecture, what we are saying is we are encoding our inputs with its previous state, and based on this encoding value, I'm trying to predict my output. So this is the crux of usually of a typical RNN, where actually this encoding decoding part is happening. Okay, because we want to predict the next statement. Okay, now let's try to see some example, try to build an intuition out how actually this encoder decoder play into picture. Okay, maybe this might be very intuitive, or maybe you have seen the sequence learning problem through this, so you can't see the encoding decoding, but now we can give a proper example for this. So let's go here. So where um, our task is image caption. Okay, so what I am doing here, my this thing will be, let's just forget about this option 2 as of now. Okay, so I have this image. Okay, now I have to predict that this image in which a man is throwing a frisbee should come as an output here. That means my output should be a man is a man or throwing a frisbee in a park, something like that. Okay, so I just need to create this output kind of thing, right? So here I have to, so here the data is typically different. Here my input is actually an image and output is basically a text, and not any text, it's a sequence text, right? So I'm just generating a sequence. So I want my model to generate a sequence. It should not say only a word, it should say that the meaning of that image as a sequence of words, right? So this is what I want to do. So this is the image capturing problem. So here, what is the, so where the encoding decoding part will come into picture. So let's try to understand it, how it is working. So what we are doing, first part, uh, so we have an image, we passing to the CNN, it is doing some computation and it is giving me a certain intermediate states after applying this CNN. So if you can see here, it's written FC7, that is some fully connected layer. So if you have seen already in the course, you have seen that um, already have seen that after convolution layer you have a few sets of fully connected layer, right? So you pick one of the fully connected layer. Maybe in this case you may have 7 fully connected layers, so you're taking the maybe the last fully connected layer before classifying it, right? So you take that as one of the state, it will take it as starting state. Okay, then you pass down as one of as an initial state to the RNN now. Okay, now, so once you part as the RNN, now now my task is, not my RNN task is, based on whatever the features I'm getting here, I should try predicting some word towards it. Okay, so I will maybe start with go, and based on my initial state coming from CNN, I will predict my state S1. Okay, and based on that I will try to predict my word A. Okay, based on here, then I will apply loss function, some loss function, and based on that I will see that whatever loss is happening, and I try to correct my states here in the state S1 and S0, right? After this, again I will go to the, I will take A as input, what is my predicted output. Okay, again I will try to create the S2 as a hidden state. Okay, so once I'm trying to create, I will consider S1 and S2 SO0 both. Okay, after this, and I will try, based on these two value and this current input A, I will try to predict man value, and then followed by loss function, right? So it is simple typical loss function, and all this part is happening, and follow which after so here we don't have put any restriction, we don't know how many layers it needed, we just saying that some output it should come, some number of words it should create, right? So it will keep on doing till it feels like it has to stop at certain point of time. So it will keep on creating, generating words and all, and it will compare with the loss function, because we will obviously have a ground truth value. Okay, so this is one of the option one, sorry, this is option one, where I just passing my the CNN value or the fully connected layer value, the features of the image, only once at the state 0. Okay, this is only one time doing. I'm now doing with red. Okay, now I have another option. What option I have? Instead of passing the image only values features as only once, what I will do, I will keep on adding it as an input along with the word that I'm trying to predict, or whatever words I'm trying to give as an input. Okay, so at, let's say at go as a keyword, I'm trying to pass my image feature value again. After with at a man. Okay, so at all these inputs that I'm trying to give, I'm trying to pass an image value also, because this, why I'm doing this, because if I just pass this image as only at this initial state, my, because of transformation, my features will be get morphed. Okay, it will be transformed. Okay, so so initial image that we want to have, it might will go so much changes that the states might not able to predict the correct next word properly, right? So that's why there's another option where the along with passing a state 0, it will also passing this image features along with each of the input. Okay, so once that part is done, uh, it will try to predict the image. So this part is there. So how we will see this part as an encoder decoder, right? So encoder decoder part will look like this, where encoding part is mostly focusing on encoding this image. This is the one part. Okay, now decoder, what decoder is doing actually here is trying to predict based on the image data, and obviously here I'm just giving directly to SO, but obviously you can give it like the second option where you're passing this as input to all of the other hidden states as well, right? So that option is also available. So once you do that, the decoder part, which is basically RNN, is trying to predict the image, try to capture an image one step at a time. Okay, so again you have to keep on understanding that how the prediction that it is trying to do here, right? It's not only because of image but also on the state of the words that it's trying to predict. Okay, so if we just say a man, just say it like that, it will not stop here. It has to stop at certain level. So it will not, RN will understand that a man cannot be a full sentence for him. So it will try to say, maybe it will add throw word here, throwing. Then it will like, then the word, it might be a man throwing, right? The RN still feel like something is incomplete, right? That is what it's trying to train. So it will feel complete. So till the whole sentence is complete, it will try to keep on predicting the words. Okay, so that is the concept of encoder decoder in the concept of image captioning. But what today we are going to do is something as a code we will actually do with the transliteration. Let me show what is transliteration will mean like. Okay, we are we are going to show something called as machine transliteration. Say transliteration. Okay, so in the code, so what it does mean that I have a word India, I just need to convert it to Hindi. Okay, so India, yeah, something like that. If my Hindi is bad, I guess. Okay, so I just want to convert it to Hindi. So what I will do, I will try to break these words one by one. That is in INDA, and I will try to predict the outputs as individual Hindi characters. That's A, say E, the small bindu of ma ki matra, in, D, E ki matra, ya, and the A, right? So this is transliteration. Okay, so this is what we're trying to predict here as a as one of a uh, as a machine translation. We will see that as a fully code. Okay, now before doing this, before understanding, let's take a one step ahead where we can set much better. Okay, so this is called as machine translation. If you understand this transliteration, this is a smaller part of it. Okay, so my input is I am going home, and my output is मैं घर जा रहा हूँ. Okay, so this problem is called as sequence to sequence problem. That means I have a sequence, and then I'm trying to predict a sequence. Okay, and that sequence can be of another language also, that is totally fine, but I'm trying to predict a sequence also. If you can see, I have only 4 words in English, but in 5 I have 5 words in Hindi, right? So this is what I'm trying to predict it. So how encoder decoder will play here? So what it will try to do is, this is my input, I am going to home. Okay, this is my x1 x2 input. It will create a hidden state, and obviously it's a basic RN. it will create a hidden state for each other, and all the states, like I am will be dependent on its previous states. Like that's how RNN works. Now what it will try to do, um, it will take this the last hidden state, or maybe the other ways also. But for this example, let's assume that it takes the last hidden state, which is a combination of all the previous states. It is taking the whole sentence into the picture, and it is trying to add as 0 to the decoder part. So we have already encoded our English sentence. Okay, so encoded our English sentence. I am going home to. Now it's time for our decoder to decode it into a Hindi sentence. So what it will try to do, it will take it will start with this hidden state as a input, and again it will try to predict for each and every word, right? So again, even for this, we might think that we know by looking at it, we know that for a single word we are predicting 5 words, right? So how the RNN should know that I should have 5 number of states, right? It is not something we can just state it, right? For each input, the number of hidden states for a uh, for an RNN will be different. So what actually we do in coding part is, just a minute. So maybe what I can do is, I can define the max number of states that I want to have. So for example, um, so in English, I know that it will, for 4 letter word is 5, right? But what if I just try to create 256 hidden states, okay, which are connected to each other? So this will be my input, like this, and will be my output. So this is my hidden state, input, output. So what we'll do in practice, actual practice, I will show in code also, that we will assume that this is the max length of the statement would be like, okay, maybe 256, 512, something like that, and it will try to run the RNN based in this 256 hidden states. Now RNN automatically will try to figure out if the less number of states are required, it will stop till that particular state. So let's say in this case I have 256 hidden states, but I need only 5 hidden states. Okay, so what I will do, I will just try to, my RNN will try to figure out only I need 5 hidden states, so it will stop till this part and it will ignore this part. Okay, RNN will ignore it properly, so we don't have to actually worry about it. It will automatically take care. So if RNN understand that it requires only 5 states, 10 states out of the 256 states, so it will just take that number of states for computation. It will stop. Okay, so this is what automatically it will do. PyTorch and TensorFlow will handle it automatically. So we will not go to maths towards how it is actually identifying, but it can be taken care automatically by the PyTorch framework or the TensorFlow framework. Okay, so what it is happening here, again going to this, what the RNN will try to find, that it will try to relate I with मैं, okay, am with whom, okay, and going to जा रहा, these 2 words, and home means घर. See, even the structure is different, and for each word we have different number of for each English word we have maybe multiple number of Hindi words, or maybe vice versa, right? So that is one thing that's trying to understand it. So while giving as an input to the RNN, we have to give vocabulary. We just a minute. Yeah, so we have to provide vocabulary for both English and Hindi words. Okay, so what it will try to encode these words to a certain format, maybe in dictionary or somewhere. And when RN is trying to train, RN will try to refer will refer this vocabulary. This vocabulary it will try to refer to predict the sentence. Okay, so that's what how the RNN works. uh, so again, why I'm telling RNN is much about, because in this case of machine translation, both in the both places RNN or LSTM or GRE will come into picture. Okay, so when it is giving me as an input, when I'm going at the decoder part, here I'm giving an English statement, kind of English word as it will check the vocabulary. You try to see that, try to map the vocabulary, any word from the vocabulary randomly to this word I, and it will try to see based on the, obviously it is based on the trained data, that it whether it's matches or not, right? And based on that it try to predict it. So it's basic, when we are doing, it's basically it's a classification problem, and eventually it's a classification problem, because in my vocabulary मैं घर जा रहा हूँ will be present vocabulary. I just need to predict that I should be followed for मैं, and घर will be followed for whom. So that is one thing, that it will try to predict it. Okay, it's not something it's making on its own. Based on the vocabulary that is present in present for the RNA, you try to predict those values. Okay, now if this part is clear to you, I'll just introduce one more component, which is called as attention mechanism, and then follow that we'll go to the code. Okay, so this new attention mechanism come into picture, which is simply like this. Now what we are saying, that मैं घर जा, let's suppose here the input is reverse, here I am saying मैं घर जा रहा हूँ, and I need to predict as I am going home, right? So the question is, do I need to pass all the hidden states, or I should pass the hidden states which are actually relevant for the input to the output? Okay, so what I'm trying to say here is, so let's say my first word is I as a predicted output. Now after this, shall I need to pass on all the hidden states again, this all the 5 hidden states, or I should take only that those hidden states which might be actually useful for me to predict the next word? Okay, so in this case, if I'm giving I as an input, again I will try to say that in Hindi I have मैं is there. Okay, so I will try to give maybe much more attention to this particular hidden state of मैं rather than any of those words. Okay, so I will just keep, maybe I will give some value of 0 1 as it is, and others I will try to give 0 0 0. Okay, that is one way, and I will try to pass this attention or this hidden state to uh, the input along with this I. Okay, once I'm able to take a particular hidden state from the input, or particular number of hidden state from the input, it is easy for me to predict the next output rather than considering all the input, right? So this is what attention mechanism, that is I will try to take specific input into consideration, okay, to predict my next output. Okay, this is what simple attention mechanism will come into picture. It will assign some alpha alpha as a value for each hidden state. Okay, some alpha value to each of these hidden state, and where it will say that maybe let's say between 0 to 1 I have 5 words, right? So let's say I have 1.1, 0.2, 0.5, 0.6, sorry, 0.1, it's already 0.1. Okay, so I have 5 words, so I might assign this 5 values to each of the hidden state, and I know that this, for the next input output to generate, I need to focus on my third word. Okay, so maybe in the third word is ja raha, ja. Okay, so I might consider this word and try to pass it on to my next input. So that's how it is trying to give me much better. It will reduce my computation to a good extent. Also it will ask me to selectively focus on particular values. Now the question is, if how should I know that which word to select, right? That's where the RNN, the training part, will come into picture, where it will try to learn the weights of this attention mechanism as well. till now we are actually calculating only weights and biases. Right now with in this it will also calculate some particular equation. I'm not going to maths part, I'm just giving an overview here. So it will also try to calculate. Attention mechanism is also a kind of set of vectors, okay, for each hidden vector. So it will try to calculate and it try to adjust based on the back propagation. Okay, so these are the few things that I want to discuss as of now. um, yeah, so what we'll do, we will do a machine transliteration, same with attention mechanism also, where um, my job is, if I give a word India in English, I need to convert to a Hindi word. Okay, so I will take each word individually, and based on my each word I will try to predict sorry, I will try to predict each individual letter, word or letter, um, in each letter in the Hindi part. Okay, that is my task would be like. Okay, as of now, any question with respect to encoder decoder in theory aspect, because I didn't went to maths, I just gave you overview of this. Maybe once I show the code, maybe you can get little bit better understanding for that. But if you have any question, please let me know. Okay, so maybe I will just go through the go to the uh, theory part, sorry, code part, and then we'll start discussing what kind of data would be. I will just go give you a setup, maybe after that few minutes break, and then we'll start coding the our basic encoder decoder model, and I will show you a variation of encoder decoder model with attention mechanism, where we will choose only specific input content to predict our next output. Okay, so that is what we're going to do here. Okay, let me stop sharing. Okay, okay, cool. um, so here we are, I'm just trying to go to the code. Okay, so actually I'm running this code in the background. um, okay, let me check one more time, code is running it, yeah, fine. This screen. Okay, so what I'm trying to this code is running right now because it takes a lot of time, but I will show you go through the basic stuff here so that we can understand. So let me share it first. I'm just putting the chat box. Cool. Okay, so what we're going to do today is machine transliteration. Okay, so maybe just I just put it here also better. Machine transliteration using encoder decoder of GRU. GRU is gated recurrent network. Um, what is the U part? GRU, gated recurrent network only, right? Or units, gate and recurrent units, I guess. I need to check this part, but this is what we're going to do. Okay, so what we're going to do here, let's see the training data. Based on that, I will maybe able to understand you better. Okay, why it's not opening? Just a minute. Yeah. Okay, I'll just increase the font size here. Okay, I hope you can see it clearly, this part. So what we so we have one data set, news to 2012 kind of thing. It's a popular data set for machine transliteration for Hindi, English and other languages. So what we have is, we have some, it is written in XML format is one of the format here, and it has one source name which is written in English, and it is also written as a Hindi as well, right? So it is given input as Adi in this case as English, and it's also written Adi as Hindi, right? So this is our basically data will be like, we will taking this whole XML file, and we will consider each of the English name, and we will try to train our encoder decoder using the GRU network, which is a form of the recurrent neural network. We will take this, and I said or Adbhut. So the different words are there. There's like academy, accommodation. So it is written in English and Hindi. Okay, so this is the kind of data set we have. So we have two. So we have test data set, training data set. Test data set contains 1,000 such instances, and training. I think training has maybe around 20,000 data set points. Okay, I think it's very big file, so it's not loading maybe here, but training file will be also look like this. So you will have something called name ID, and since it's XML format, so it is written as a code source name. In between the source name or slash source name, that is the input you're giving your English words, and then followed by a Hindi word. Okay, so our task would be to train on these datas, English, and try to map English and Hindi words based on that, and try to predict our this test data, where I will give this English word as an input and try to predict the Hindi word. Okay, so this is our uh, goal will be in today's this code part. Okay, so it is already connected and it's running here. I'm just go through the basic steps right now, and I will code only the encoder decoder part, because here there the line by line steps will be much better to understand. So I will do that part, and maybe by that time, so let's talk about this. So we have some certain important functions. We are using PyTorch in this case, PyTorch, and torch.nn for creating our neural networks, Optim for optimizers like stochastic gradient descent like that. Okay, something called autograd is there, and these are all related to the creation of our basic neural networks. Okay, here ideally I'm using CPU right now, but we can change, you can play with here and change to GPU as well if you want to run your code in GPU. This is Google Colab, so you can play with GPU as well, but right now it's running on a CPU. And then some we are using matplotlib, Seaborn, IPython for showing our outputs. Okay, okay, so let's start with our setup. So what, so we have two things here. We have English words, in English words, basically English letters and Hindi letters. So what in this part of word we are doing is, we are defining all the English alphabets right now. So we are here right now, we are taking only capital words, we are converting every word into capital words, whatever input we are taking, and then we are having one padding character as special character. Okay, and then we are converting and assigning each of these values um, to a particular um, we are assigning each of these values uh, to particular number. Okay, okay, I can't run this, right? Okay, let me stop the progress, maybe. That will be much better. um, just a minute, I'll just stop it because I have removed the outputs. I should not have done that, but it's okay, we can run it later. um, so okay, so this is the output we'll look at. So here what we're trying to do is, for each letter we are assigning up integer value to it, like this A, B, C, D. So for that, 1 2 3 4 5 6, so we have 26 letters along with a pad character, so we have 27 characters from the English alphabet. Okay, now for Hindi, we have according to the this, we have something called as Unicode hex range. So in that we have assigned certain range from here. So what we're going to do, based on that, we'll try to assign our each Hindi alphabet into a particular number, similar like our English thing. So there are multiple matras and words are there. So total we have in Hindi alphabets, we have total based on that 129 words. Okay, so 129 letters along with the pad. So we have this. So we have taken this code just to create our indexes, right? So for each letter we are creating an index, because after this, once we get this index, we try to um, what we'll do, we try to combine them to form a word. Okay, so for this the this part is simple. So what we're doing is, apart this in English alphabet, we are trying to put pad character as 0, this pad character, and we are going to so we are calling a for loop where we are going with each and every English word character, sorry, English character, and we are giving an index. So index starting on 0, so from that index plus 1, that is 1 2 3 4, that indexing that you can see here we're trying to assign, right? Similarly, for same thing we have done for Hindi word as well. Okay, so once we have each English and Hindi characters assigned to a particular index, now what we do certain pre-processing. So this pre-processing will be done on this kind of data. On this data we're trying to do certain pre-processing. Okay, because you can see here there's lot of um, uh, words and letters are written in English, sorry, in blue and orange color. We don't want that, only need the words written in white color, right? So that is input and output. We don't care about any other thing. So we will try to do certain pre-processing to remove all the other part and only keep the English and its equivalent Hindi word. To do that, first what we're doing is we're trying to remove some basic characters from the input. So what we're doing, so to do this we have something called a regex. So regex is one of the popular uh, data pre-processing tool for text. So from this we are trying to extract only words which are belong to English characters or Hindi characters. Okay, so what we are actually doing in this part of code is we are removing uh, any such line. So we are replacing, so if there I have some hyphen or some comma present in my input, I'll just giving replacing with a simple space. Okay, and also I'm converting each of the character to the upper capital letter, because we are dealing with only capital letters as of now. Okay, so this is one part. In Hindi also we are doing same. We are taking with hyphen and the comma, and we are just cleaning this part of the, like, wherever this comma word will come into picture, we will just replace it with space. Okay, so this is what we are trying to do here, only removing some comma, semicolons and all those part. Now this is the important function, this part. So this part is an important function. So what we are doing is, maybe I will not go to line by line code, but I will just tell you what it's trying to do. It is trying to do is, we are having a parser from XML. So whatever the data we are having, this part that I'm highlighting right now on my left hand side, it is actually a XML file, right? The data is written in XML file. So what we're trying to do, we're trying to read this XML data set one by one and try to remove those tags. So these tags are there, right? Like source name, target name. These tags I'm trying to remove. I'm trying to remove this IDs and all. Okay, so this part I'm trying to remove from here. So that is one part I'm trying to do. I'm cleaning my vocabulary also. So wherever this hyphen and commas are present in the data set, I'm trying to remove. So this is one part I'm doing. Another part which I'm trying to do is I'm trying to skip the noisy data. How the noisy data will look like, I will let you know. By looking you will get a better understanding. Also, another important thing what we're doing, using the torch util in data, that is data set, what we're trying to create, we're trying to so when we're trying to uh, take inputs, we are trying to do that in the terms of batches, right? So I will not take all the 20,000 words directly as an input to this. I will take maybe 16 or 20 words of batches as an input and try to train my data, right? So similarly for this part, this init function get item random sample, so it is randomly shuffling my data and taking my some random batch of inputs from there and try to pass it on to me, right? So get batch and get batch from array, it deals with that. So let me run this part as well. Okay, so this is a transliteration data loader. So the main purpose of this data set itself to clean up my data, also to take batches of data, certain batches of data smallly, so that I can use them for training. So I have train data and test data already, files is there. After the session is over, while uploading my code, I will share these files with you as well. Okay, so I will run this part as well. So what here we talk about, some noisy data might be present in a data set, right? So what are those? So here the output of this. So what is there, that so there will be certain words, English words or Hindi words, where the proper connection has not been there, the input output are wrong. So let's say Barharwa junction, Barharwa junction, it's written in English. In Hindi it's only Barharwa, it's not junction. It's like State Bank of Travancore is written properly in Hindi but not in English. So this kind of certain noisy data is there. We're just trying to remove that because it will not help us in our training data. Okay, so that kind of this thing there, like debug valley. So debug valley here, it actually has to be two separate words, but it's combined as a one single word. Or Nagar road, so it is written Azam Nagar, not the road. So these are noisy data. We try to remove it from here. Okay, and if we just want to say how much data we are going to deal with, so we are dealing with uh, training size of 20,000, 20,500 and test size of 1000 words. So how the train set data look like? So we have one train data and it's in English, and it's equivalent Hindi word we're trying to put as a output, right? Then Myron, Khwab kind of thing in English and Hindi word respectively. So we are trying to do it just by calling simple random function, and we are trying to using that this function that we are defined so many functions. Here we are just trying to call some random samples. From that random samples we are trying to print this 10 datas. Okay, now this part is done. So we have our data set ready, we have done all the pre-processing. Now the next step is to encode it. We have to encode into a certain number. So how to do that? So to do this, basically what we are doing is we're applying something called as one hot encoding. Okay, so I think you have came across one hot encoding already by now, where what we're trying to do is we have a set of vocabulary like A to Z. So if A is there, so I will keep 1 at A position and rest of the other indexes I will keep 0, right? So similarly for words also, if I have certain word, I will create a whole set of vocabulary. So maybe let's say I have 100 words in my vocabulary, so I have a vector of 100 in elements, and wherever the index, let's say in that particular Khwab is there, right? The Khwab is at index 50, so at index 50 I will keep 1 of that Khwab and rest of the other words I will keep 0. So that is one hot encoding, and this is what we are trying to do it here. Okay, so we are asking the letter index uh, at 0 dimension, and we are trying to provide the one hot encoding. The pad pose is for one hot encoding part. Okay, so this is what we are trying to do for word and the so for both English and Hindi part. So I will try to run this. So this part will deals with one hot encoding, and I will just show you how it will work for G. This is for, how it will work for both. GT is ground truth. Okay, just let me write it down. GT is ground truth. Okay, so ground truth is basically Hindi words. Okay, so I'll just so this part of the code just show for one English word and its representation, respective representation, and it will show for Hindi. Okay, so the Hindi word is the word that we are dealing with is Shraddhanjali. So Shraddhanjali consists of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it has 12 letters in this Shraddhanjali word. So based on that, this is the one hot encoding. So here you can see particular one word that you can see here. It's basically it's for one letter that we're talking about, right? So like A is the has index 2, so the SRHA, this is A part where that position 2 it is keeping as 1, so this is called one hot encoding. And in Hindi we are getting a simple numbers because we are trying to predict the output, right? So we just need a number, not as a one hot encoding. We just need to say that out of this 100 word and 100 characters, which characters belong to which English character, right? So that is what we're trying to do as a mapping, proper mapping. Okay, so I think I will stop here maybe for a minute of time so that you can go through this part, so that I will start writing the encoder decoder part of the GRU. Okay, I will take a break of 5 minutes. Maybe you can ask me a question in the meantime, or you can type on chat box. Maybe we'll come at 7:02. Okay, and then we'll starting writing the code of decoder using GRU, and let's see that how it will going to work out for us. Okay, so this is, I just want to cover this encoder decoder part with encoder decoder attention part. This part we are going to talk about, and follow it we will do the training part. Okay, so we just train the model. It will not complete in this time, but I will just show you the intermediate output for this part. Okay, so if you have any other question apart from this, you can also ask me. um, Otherwise we will take a break till 7:02. Okay, um, welcome back. I will start coding. Uh, in the meantime, I'm explaining what are the things that I'm going to do. So, uh, like as I said earlier, um, if any RN network, any word, right? So you're trying to create a sequence to sequence problem, right? So each English word character you have to translate into a Hindi word, right? So how to do that? Like how much number of output will be? Like we have seen, right? The number of characters in an English word might be more or less to a Hindi character or word, right? So how to so we have to put certain restriction that till where the RNN has to go, or the a particular GRU, in this case GRU network to has to go, right? So for that we defining that in particular output, the number, the whatever the output we are going to have, maximize it can have till 30 characters. So if any input where if you're going more than 30 characters, we are going to stop it. We are not going to deal with those words. Only we're going to deal with words where max to max, if the translation is happening, it should go till only 30 characters. This is what we are trying to define using um, max output char. Another important thing, now we will start uh, with transliteration class. So usually if you have attended earlier session also, we usually define a particular class uh, for for each of the modules that we're trying to create, right? So we will define transliteration, um, literation, encoder-decoder. Okay, so we are defining that part, and end module is for to tell that that we are going to we are defining a particular neural network here, right? So first part will obviously be defined as an initialization function. We are passing self as a variable. We'll have something called as input size, hidden size, and output size. So what we are trying to define here is we are trying to define maximum number of input output characters that are uh, our input layer, hidden layer, output layer can take. So this is what we're trying to define it here, and we're calling them superclass transliteration, encoder, decoder, and self, calling it, and then we are calling initialization. So what we are doing is from transliteration encoder decoder function, we're trying to call NN module here. So that's a constructor here. Maybe you don't have to much focus upon that, but right now here we are defining our hidden sizes. So hidden size is basically the number of characters it was take in this case. Similarly for output size, we are going to do that. Output size, okay, hidden. Okay, this part is done. Now let's define our encoder. So the beauty of PyTorch is you just need to tell encoder as a word, and then you have to tell which type of cell you want. So here we are taking one RNN cell. Okay, so we are saying cell dot encoder RNN cell as one encoder cell as nn.gru input size and hidden size. Okay, then again one decoder self.decoder RNN cell, and we're defining again in GRU where we're taking output size and hidden size as a variable. So what is this NNGRU, right? So maybe you can just write NN.GRU PyTorch. So you can go to the PyTorch documentation and see that how it is going to work out. So it gives all the basic details on the input side, the number of expected feature input x, the number of feature in the hidden state, and number of layers, different type of whatever the different type of parameters that we're passing. All this information will be given here, right? So while coding, please refer PyTorch side by side. Okay, let's get back to our this thing. So we have created we have created one encoder and we have created one decoder. Okay, you just need to define this line, that's it, no more, nothing more you have to do. Then after encoder decoder we have to find hidden to output. So this one layer we are trying to create, that is last layer, where we are trying to predict which character should be it should be there. So we are defining n and hidden. This is basically a fully connected layer. So hidden, we're giving input as hidden size and output size, this we are passing, and the which is basically a softmax layer. This above is to hidden to output, basically the final layer will be softmax layer. So we write as nn dot log softmax, and dimension we are giving as 2. Okay, so uh, sorry, output size. So we defined our whole this thing, and there's something called verbose. Verbose is kind of command which keeps tracks of all the intermediate and uh, intermediate input layers, variable sizes and all that. Okay, so what are the intermediate values that we get are basically in the tapes or in the in the terms of what is the size of a particular hidden layer, output layer and all that. It is we keep track that using verbose as a keyword. Okay, so we have defined the initialization function. Now let's define the forward function, the feed forward function, that not feed forward, the simple forward function that we do. Okay, so here we define self as a uh, class variable name, not variable, class object. We'll pass the input, we'll pass max output char, that the number of characters I need to predict max to max. So I will just write max output chars. Okay, I'm telling my device where I need to use CPU. You can, if you write GPU also, that is totally fine. And there's something called as ground truth. Okay, so what we're doing here, okay, so there's two options basically. Just a minute, let me complete this. Max output char. Okay, sorry. Okay, so what do we know, ground truth, right? So what happens that uh, after each and every letter you're trying to predict a word, right? Now they have two options after predicting the word, or sorry, predicting a letter in this case, right? Either you take that predicted letter as which came as output again as an input to the next state, or you can consider the ground truth directly, right? Ground truth means directly, instead of whatever the predicted output will be, let it be there, but you consider the ground truth, and based on that you pass that as an input. So let's say I have I as a first output, right? Now after first output, either I can take this as a output as my second input, or if my ground truth is like, let's say n, this is my ground truth, that this is the actual word it should be. So what I will try to do, I can take this second input. Okay, so if I put ground truth equal to none, that means uh, I will not take this input. I will whatever the output I am taking, I will taking this as a input, the subsequent input. So this is what I'm trying to do. So whatever the output I'm getting, I'm taking as second input, whatever the subsequent input there. Okay, rather than taking directly from my ground truth data, I'm just taking from the whatever predicted data I'm having. So this is what ground truth is means by. So once that's part, so we're keeping as none right now. So let's define the encoder now. So we have encoder, uh, so let's call the encoder, not defining, we already defined it in the above init function. So out hidden self dot encoder rnn self, and we are passing as input, which give us input hidden and output state. So what we are calling self dot encoder RNN self. So this is when we are calling this line, writing this line, it is calling this GRU encoder. Okay, here we are passing only as a input as this thing. Hidden size will be some by default hidden size we are taking, and output will be some out and hidden. Okay, these are the intermediate states that I'm trying to get. This is my encoder, and if I want to print what is my size of my input and output in this case, so I can write as encoder input dot shape, and then encoder output out dot shape, and print encoder hidden dot shape. So I'm just trying to print out my intermediate sizes. I will just show you once while we're running this where this verbose will come into picture. Then we're calling decoder. Once we encoded our input, let's call the decoder. And so decoder state is, so when we're saying decoder, so we are saying that uh, from where we should start. So we're starting with hidden, that hidden as a S0 that we are taking, right? So we are taking hidden as a starting point, and then decoder input will be, we are defining dots or zero, which we're taking as hot one hot encoding. So dot 0 1 1 self dot output size to device. Okay, so so what we're doing now, whatever the input we're going to take as a in the decoder, we'll converting that as a one hot encoder. One hot encoding. We are performing this step here, and we are putting some output in the output. We are creating a list as a list. Okay, then after decoder, the same thing we can write here. So let me copy some part. So we again will call this part, and then to check the size of the hidden state, decoder state will print this, and decoder input. So decoder underscore state and decoder input. Okay, so we're just printing this part, few of the parts here. Now what we'll do, we'll go one by one in each of the characters. Okay, we'll go one by one here. So and then we'll try to call decoder here, decoder state self dot decoder RNN self, and we're giving decoder input and decoder state. Okay, so once we're getting certain output, and we are just printing that state, particular hidden state value. So print decoder intermediate output out dot shape. Okay, so once we this part, now what till here we have done the so using decoder, so we have come to the hidden state of decoder. Okay, so we have whatever the input we came from encoder and plus input, we reach a hidden state here. Okay, that which we call as decoder state. So once we get that part, then Now we are going for prediction part. So we are calling h2o hidden to output, and we are passing this decoder state where it will the fully connected layer or the linear layer will try to predict, and then based on the whatever the output we are getting, we are applying this softmax function there, and so we will get certain output. And now we are just appending that part as we are just flattening this um, output to a single vector. So once we did that, then we'll print self.verbose again, and we'll print decoder output. Then so we are just printing the shapes only once, so we are just keeping it false after showing this part, and it will keep on continuing for each and every character. Okay, and then we are just storing all these values. So we are trying to find the from the output this out character, so we are trying to count the maximum, what is the maximum value we can get from that vector. So using toss.argmax we pass that and keep dim equal to 2 if ground truth. So whatever the output that we are getting is none. Okay, is not ground truth is none, then max idx ground truth I dot reshape 1 comma 1 comma. Okay, I will just tell you what we are doing here. So in case our output is the whatever the output we are getting is actually is not present in any of the ground truth, right? So you try to reshape the max idx, and it will try to give uh, a, a one simple non value to this. Okay, so but if it is true that the word that is predicted is present in the ground truth, so what will do it do a one cohort encoding again. So toss dot float tensor out dot shape to device 1 hot 0 and scatter. So whatever the last three lines I'm writing, just to put them in a certain format. Okay, and decoder input dot detach. Okay, let me explain what we're doing. Just let me complete the code, it's almost done. And okay, do this, I just need to do return outputs. Okay, so what we have done here, so so we have defined our layers. Okay, so we have defined our encoder layer, hidden layer with one single GRU layers, follow that one layer of followed by one fully connected layer, and the last layer is a softmax layer. These four layers we have defined. Now what we're doing, given an input, we are applying an encoder on top of that cell. Then we are calling the decoder there. From the encoder, that hidden output we are taking as an input here. Now for each and every character in this loop, so it will go for each and every character from the input, and it will take input and the decoder state, the state which is coming from encoder, it will take that and state and try to calculate the predicted output for a particular character. It will predict a particular character. particular character in Hindi because our input in English, right? And it will put that into one single vector, and then it will try to find so it will be a particular array. So out it's basically one particular array, long array. From that it is trying to identify the which character is actually the decoder has predicted, and it is trying to keep that in a particular one hot format. Now what here the last line is doing is hot dot detach is the while doing back propagation it will not touch the decoder input. So we have sent, right? So whatever the output that we are getting from one of the decoder, we are passing that as an input to the we're passing that as subsequent input. So there we are not following back propagation because that's the output we want to give as inputs. We don't want to change anything in that. So for that we just say that for decoder input we're just saying back propagation is disabled for that particular decoder input. Okay, so this part is done almost, and another function I will just write it down. After that most of the function is written because same process we are going to pass out for other things as well. Okay, so only one function. Now what we have to define is one infer function. Okay, so where we are trying to call, we'll do just one pass of this and try to identify that given input what is the intermediate output shapes that we are getting. Okay, that is much more needed for us because when you're trying to code we have to see that all the dimensions are correct in picture, because that's where the most of the issues will come when you're trying to train a model. Device is equal to CPU. So I'm just writing a simple code here. So I just call net.eval to device. So I'm putting my network into evaluation mode, inference mode, and what I'm doing, I'm just passing one word in one hot vector format, word, which is the input, and I'm passing also the indexing of English letters that we have done earlier. Sorry, alpha. And then we are predicting the output net word one hot encoder max output char, and just return the output. So what it will look like I'll just tell you. So let's run this part also. Okay, so now our main thing will be, so we have defined one network here, one typical encoder decoder network. Okay, then what we are trying to do, we are calling this class translation encoder decoder, that transliteration encoder decoder that we have defined here. We're calling it, and we are passing the length of the vocabulary. Basically this is a vocabulary here, that is A123. You can see the output here, right? A equal to 1, B equal to 2, like this. Hidden size as well as our Hindi character words. Okay, so these two words we are trying to do, and we're passing this our hidden size we are passing, and verbose equal to 2. That means if we do verbose equal to 2, we will check the input hidden states and the shape of the each input and say encoder and decoder output. So once we run this part, now we have defined this infer function. So let's see output. So what we are giving input as the network that we defined here, we are giving input as India, and maximum character output that we want is 30. That's more than that. Okay, some issue is there. H2O. Okay, I might have written something wrong here. Okay, let's keep it like this. Just give me a minute. I just attach my charger. Yeah. Okay, so let's see what this infer function give us as output. So what is given is, so for given an encoder, if I'm giving an input it is giving the size of the tensor that I'm trying to build. Similarly for encoder output, encoder hidden state, okay, decoder state, decoder input, and decoder intermediate output, and the decoder finally output. So this is the shape. So whenever we're calling this verbose, right, decoder input output shape, just telling the size of the vector that is, or size of the vector is trying to generate. Okay, so this is what infer is trying to do. Now what we have done is, when we're calling infer, we are putting this network of encoder decoder in the evaluation mode. We haven't trained any data, but we are putting in evaluation mode and passing this India as an input, and based on the input it is encoding and try to decode certain words out of it. So let's see what is trying to decode. So if I run this part, okay, I think just a minute. Okay, so nothing, without doing anything, it's just trying to give pass out as, uh, just based on the encoder decoder part, it's just trying to pass out this part as only one vector, that is a. Okay, it just passing as output, because Rn is assuming that this is what my output should look like, so it is passing only one thing. Okay, this part is done. Let me check the code once before running this part. um, okay, cool. So only one thing, same code with only attention part, right? So I'm just going to introduce this attention part here, because what we are trying to say in attention part, instead of looking at the whole, each and every character, whole characters of the whole word, we should start giving attention to only particular characters which are important for us for next prediction. So this is what we're trying to do. So to do that, this part is all, everything is same. Only thing that we are trying to do here is, okay, um, only thing we are trying to do here is, we are calling one attention function. Okay, using this linear function. So what we are trying to do, we are trying to define a particular certain vectors which can calculate that which character from this input I should consider for my next input as a decoder, right? So this encoder input, decoder inputs are two different things, right? So for decoder input I need certain characters from the encoder input which I should consider for my further computation. So this is what I'm trying to do here. So I'm defining this one at self dot attention layer, uh, one layer with respect to it, and try to predict output it. Now what else I'm doing here any different? Okay, so another different thing what I'm trying to do here is this part. Let me run this part. So another difference that I'm trying to bring here is encoder decoder state. I'm just assigning the attention network. So attention network will be calling using these three parts. Okay, so it is based on the encoder output and decoder state, it try to calculate W, and based on that it will applying a tanh function on top of that to get the certain weight. So it gets attention weight based on this value, and we are keeping this attention weight to it towards us. Then based on this attention weight, we are giving this to as a decoder, as a part of the decoder input, and we're trying to start calculating the stuff. Okay, rest of the code is almost same as whatever we have written earlier. So once we do this, let's try to run this part, transliteration with attention coder. So if we try to run this part, okay, so here what we're doing, encoder decoder states will be almost same as earlier. Now we're bringing attention to a picture, right? So I'm the part that I'm highlighting here. So what we're doing, uh, before giving as a input to the decoder, we are doing certain calculation with vectors of UVW, from which we are trying to assign certain values to each and every input hidden state, encoder input states. Okay, based on that we are getting a single value which is going to pass on to the decoder input. Okay, so that's how it will keep on adding. And once we did this part also, um, so again we run that in a eval mode, and we have seen that, so given as a input as India, as it is trying to predict the 30 30 characters that we have passed, right? Maximum it can have 30 characters. It's trying to predict how India can be written as, but it since it has not been written, it is giving some gibberish output. So let's train this part. Okay, for training I need to write certain code here, so let me write this code. Okay, so it's small code basically. So two part I am writing. So one is training setup and one is training batch. So let's write training batches. Each batch, so I'm taking each combination of Hindi and English letter. So for that I'm giving net as an input, optimizer, my loss function, my batch size. Can I add it? No. Batch size as input, device is equal to CPU and teacher force. For now just ignore this teacher force part. It's one of the criteria that we have to write. So I will call net.train to device. So I want to start the training. Okay, so I'm defining a parameter for that. From optimizers we are giving gradients and 0, initializing gradient 0, and then from English batch and Hindi batch, train data. So using get batch function that we have written earlier, from that we are extracting Hindi words and English words and its corresponding English words. So once we do that, we are defining total loss, and for I in range for the batch size. So let's say 10 batch size if we have, so 10 combinations we will have. Then input word will be, so we are now converting the particular English word to one hot encoding. So we're calling word.rep underscore rep as a function, passing the English word and the dictionary that we have created earlier with indexing, alpha to index, and the device. Then ground truth. Ground truth is basically the Hindi, so we're passing Hindi batch, then Hindi to alpha index, so Hindi index that we have created earlier, and putting them in device. Device is in this case is CPU. Okay, so once we do that, now output would be giving input network. In that input we're calling input, shape of that output, device which we are running, ground truth equal to GT if teachers force, else none. Okay, this part is done. So we are converting to one hot encoder. Then for each input output, index and output, enumerate. So we'll get multiple outputs, right? Outputs in this case is characters. For each character we'll calculate the loss, output GT index, divide by batch size. So for each batch size we are calculating for each batch size we're trying to calculate the loss, and followed which we are now calling loss.backward for backward propagation. So retain graph is one of the keywords that we have to use. During back propagation we are telling that the so there's a kind of chain rule has been happening for each of the every nodes. So we have to retain that while doing the back propagation. So we have to mention that retain graph. So once we do total loss, we'll calculate the total loss, and so that will be considered as one particular step, and we just return the total loss. Total loss divided by batch size. So we are taking average of it. So let's run this part, and one more. So this is for particular batch training, right? Now we have to define a proper train setup from which we're going to call this batch. So function is train setup. Here we are passing the network, learning rate, number of batches on which we want to train, batch size. So we have testing, so we are doing on small data, momentum, that is for optimizer, display frequency, so how many times we want to display the output after each how many iterations, and device is equal to CPU. So once we do that, net to device, so transferring our network encoder-decoder to device, we're defining our loss function as nn dot negative log likelihood. Yes, this is like this, and so negative log likelihood is basically a cross entropy in this case, and optimizer, we define optimizer here, net dot parameters, and the learning rate equal to learning rate that we are defining. So I have to add an optimizer we are using, and there is something called teacher force, where we are going to deal with the ground truth value while giving the input. So for that we are dealing with here. So this part is done, and then we're defining the loss array with np keeping the size of number of batches plus 1. So we have 100 batches, so we are keeping 101 total number of size of that particular array. Now for each batch, we're going to calculate the loss array. We'll find the loss which you're going to find from the output from here. So we are calculating here the loss here, so we are going to keep that part here in the loss array. So after this we are going to do certain calculation. Loss array of I into I plus train batch, we're calling the earlier function that we have written, and we are passing our network, optimizer, criterion, batch size, device, teacher force is equal to I is less than teacher force up to divided by I plus 1. Okay, so what we're trying to do here is basically we're passing this train batch for loss array and all, we're passing this part, and we are storing this value in the loss array. Okay, so once we do that, I am now writing the code for displaying. So we just need for displaying that how much loss has been improving or removing and all that. So just let me quickly write this part. um, for display frequency, after every 5 or 10 iteration I'm going to produce the uh, loss input, that how much loss I'm reducing and all that. So I'm clearing the output and I'm printing the iteration. I'm plotting the figure, and that plot I'm passing the loss array value 1 to I, and then I'm keep for each value I'm just printing a star in this case. Okay, we will see what this star means while looking at the output. So what thing at each input, after each iteration, we are whatever the value we are getting, uh, to put that on the plot, we're just keeping that as a star. So x label will be iteration and y label will be loss, and plt dot show. And print /n/. And then if you want to save your model, so for that you just need to write toss.save. It will save the training network and just name it as model.pt. Okay, so that you don't need to rerun it again and again. You just use toss.save, it will do that, and just return loss ARR. So let's run this part also. Now without attention it will take time, just let me do for iteration with attention. Okay, so I'm passing network with attention this part with calling this class, where I'm passing the English vocabulary, Hindi vocabulary, and the hidden size. Now using the history, I'm passing the loss history. Module number has no zero attribute. Okay, where I'm writing wrong, let me check. So somewhere I've written zeros here instead of zeros. Let me check where I have written. Here, and then loss zeros. Okay, so I think here I should write as only S. Okay, I will give you the full code with running output. Just let me run this part also, as doesn't have get batch. Okay, some other input get batch. Get batch is, so where it is running coming for me, transliteration data load has get batch. So I'm getting at net train 0 grad. Okay, net train 0 grad. Okay, get batch. So I think, okay, I should write underscore. So let me run this again. I hope this will be almost done. Yeah, now it's running. So it will take a lot of time, but we can see intermediate output with learning rate of 0.01, batches of 2000. We are keeping 2000 batch with each batch of 64, so it is going to traverse with each word multiple times. Okay, and display frequency of 10. So after every 10 iteration, it is going to show us a loss output. So let it run. It will show in few minutes and few seconds. So what we have done as of now, by the time it shows certain output, so what it's actually trying to do here is we have defined one encoder and decoder. In this case, we're defining simple encoder decoder and passing the hidden layer as a output, hidden hidden layer and the one softmax layer. Along with it, we are trying to define one attention layer here, which try to the our GRU will try to learn that which characters input character input is important for us to predicting the next output, right? So based on we have wrote the code and all that, and during training time we are passing them in terms of batches, one batch at a time. So yeah, so it is showing like this. So after 10 iterations it is showing a loss of 0.46, and you can see that how this part is changing. So after every 10 iteration this graph is going to change, and it is going to show that how it will look like. So each star value is particular for one iteration. For all the maybe 9 or 8 iteration, it is trying to show that how the loss has been changing over the period of time. So this is a good indicator for you. So if you think that the loss is not being stopped doing getting less over multiple iteration, what you can do, you can stop it and you can start looking at where I need to change my hyperparameters, or if I need to change any part of the code of my model, right? So this is the ongoing iteration where you can see that how your loss has been changing over the period of time. Okay, so it will keep running. It will maybe take a half an hour to complete all this part, but that's okay, that's not a problem for us. But this just to give to a brief example how encoder-decoder works, especially how you do with the PyTorch. So what I will do is, once this part is over, while uploading I will upload the full set of code properly with all the outputs, such that you can get a much better output results. Okay, that part is done. We almost end of the session. uh, so what I need to tell you one more thing before going is, so what you need to do from here, right? So you have seen multiple so let me stop sharing once. It will run. Okay, so let me do this. Okay, so what are the steps now? So you have done basically all this course and all that, right? So now it's part for you to now do a much more hands-on session in this case. So how you can which website you can go and try to uh, learn from this part, right? So what are the things you can do for putting hands-on? So I just give you one sample code, and it will take some time for you to get your head around, because it's still a pretty complex step that you're trying to learn. So what you can do is, there's a website called Kaggle. So let me show you again. um, Share my screen. Okay, and I need to unpin myself. I get to unpin. Yeah. Okay, so what I need, you can go is something called as Kaggle. It is by Google. Let it open. Right, so it's one of the largest community where you will try to uh, there are a lot of competitions, are there, a lot of data sets are available and all that, where you try to learn you try to improve your hands-on capability with all the problems that you're having here, right? So here you can have your own collab notebook and all everything is available, you just need to code it here, right? So a lot of competitions, data sets, models, you can check other people. It's like competitive coding, that the way you have seen the competitive coding earlier in your life, same way Kaggle is same kind of platform is there, where you can look at multiple type of models and all those stuff, and you can try to learn all this part on your own, right? So even the code llama, alpaca, llama 2, these are pretty very new models available out in the market, which we call as large language models. All this stuff you can try to learn on your own, practice it, you do a lot of hands-on, because theory is good, you should know the background, but unless until you try yourself, put your hands dirty with the code, you're not able to get it properly. So yeah, it's a pretty good website that you should try and spend your time with it once your this NPTEL course is over, right? I'll just put in the chat box. Okay, spend some time here. It's more like a competitive coding, lots of competition, and even lot of job opportunities also. Using Kaggle you can make your own profile, and then if you're trying to apply for a job and all that, at that point also you can show your Kaggle profile as well. So it's uh, pretty useful, and I would suggest everyone to try it out after this. Once this deep learning course session is over, all this part, once you get into hands-on part, you should try Kaggle competition for sure. Okay, so that being said, uh, this session is over and over from my side in this live interaction sessions, and maybe the other TA will be over within this week for that, or maybe another session for him may be available, but the crux of this whole deep learning part is, you have to understand, is that it is becoming little complex in the world that you are trying to live. Simple coding is not going to be help to you. You have to now start dealing with more complex problems, and deep learning is one such way to deal with such complex problem, right? So I hope this course will help you to achieve that part, and help you with increase your knowledge along with the job prospect or any other aspect that you are looking for while learning this course. So if you have any questions, you can ask me, otherwise the session is over from my side. Thank you everyone for coming and sticking to me for all this till all this 12 weeks, because I know uh, as you go along, the deep learning course will become more and more complex. So I really appreciate that you attended these sessions and all that. So thank you very much. So I will stop the recording also.